The circuit consists of a battery, a voltmeter, and 5 fixed resistors as shown. So this circuit is also known as a wheatstone bridge circuit, where essentially you have all the resistors arranged in a diamond-shaped circuit. When in fact this resistor can actually be rearranged in something that is less intimidating and much more familiar to what we have already seen in class. For example, if you observe the 8 ohm resistors as well as the resistor R that we need to find here, these are basically two resistors in parallel, which you can just reduce into just a single resistor. So in that case, let's just label this resistor X, where X will be equivalent to 1 over 8 plus 1 over R is equivalent to 1 over X in parallel. Okay, this one we have to do eventually towards the end. Now, this one will be your 2 ohms resistor, and then you've got another branch here. This one will be your 5 ohm, and then this one will be your 10 ohm resistor. So here, basically this is connected to a total EMF. Let's just label this as VT. So you'll get a similar, a much more familiar circuit compared to the wheatstone bridge. So using the concept of KVL that we know, studied in class, so let's just label this junction as A, and this one is B, and this one is C, and this one is D. So points VB and VD is where you have our voltmeter here. So it says here the voltmeter reading is 0. What does it mean by that? It means the potential difference between B and D, or what we call VBD, is equal to 0. This shows that the potential at B will be equivalent to the potential at D. So using KVL, okay, we can actually derive different equations according to the different loops that we have based on the circuit. So the simplest one would just be at the loop from A, B, and C. So you'll get VAB plus VBC is equivalent to the total voltage supplied by the EMF. This would be your first equation. Secondly, it will be the second loop, which is VAD plus VDC is equivalent to VT as well. Now, given that there is a bridge across the BD junction where you have V here, so we can actually go for the loop of A, B, D, and C. In this case, it will be VAB plus VBD, but since VBD is equal to 0, so we just omit that that term, and then we get VDC, and this one will be equals to the third equation. And then similarly, we use another loop, which is A, D, B, and C. So you have VAD plus VBD again is equals to 0, and this one will be VBC, this one equals to VT. So this will be your fourth equation. So now observe the similar terms that we have here, VAB and VAB, and this one is represented by VBC and VDC, and this one equals to VT. So from these two equations, we know that we can represent the terms as VBC equals to VDC in this case. So how do you find out the potential difference across the X resistors as well as the 10 ohm resistor? This one you just have to use the potential divider circuit formula, where X over 2 plus X, where the resistance of this particular resistor over the total resistance of all of the resistors in series, multiplied by the total V. In this case, we just omit it because it cancels out, and then VDC will be equal to 10 over 5 plus 10. So this is the potential divider formula, where you can get the value of the potential difference directly from just using the values of the resistance, rather than having to calculate the current manually and so on. So here you just solve for the simultaneous equation. You get here 5x plus 10x, or this one you get 15x is equivalent to 10 times 2, which is 20 plus 10x here. So here you can just rearrange. You get x equals to 4, if I'm not mistaken. Yeah, 15x, 15 minus 10, you get 5. 20 divided by 5, you get 4. So here, substitute x equals to 4. So you know 1 over 8 plus 1 over R is equivalent to 1 over 4. So some sort of mathematics that you need to do. Here you can get R is equivalent to 8 ohms, where the answer is D. That's how you get it.